So in the last hour today, we are going to learn about the geometric series of cash flows. Again, this is a topic that is mentioned in your textbook. You can read the regarding chapter in the reading assignment related to the geometric series of cash flows. So it says some economic equivalence problems involve projected cash flow patterns that are changing at an average rate f each payment period. So what does that mean? So remember, in the uniform series, in the end of every payment period, we are observing a constant amount of cash flow, which was denoted by A. Okay, so in the end of every period, there is a constant amount of cash flow in uniform series. In gradient series, if you remember, there is a linearly increasing or linearly decreasing cash flow size. For example, in the first period, base payment of A0. In the end of the second period, there is a payment A0 plus a gradient. In the end of the third period, there is a base payment plus two gradients. So in every following payment period, the gradient, based on the gradient size, the payment size are increasing or decreasing in a linear form. In geometric series of cash flows, the cash flows are going to change at an average rate of f%. So this means in the end of the next payment period, the payment is going to be f% larger or f% smaller than the payment in the previous periods. So why do we use such series of cash flows? Now, imagine a fixed amount of commodity that inflates in a price at a constant rate. Each year, it is a typical situation that can be modeled in a geometric sequence of cash flows. For example, assume that the interest rate is 10%. I'm sorry, not interest. The inflation rate is 10%. If the inflation rate is 10%, then the price of a commodity that is $100 today is going to be $110 worth 1 year from now, right? Because of the inflation. And the next year it will become $121. Why? Because it is going to increase its price based on the inflation rate and that price in the end of that year. So imagine now, every year you are purchasing this same product again and again. In the end of every year, you are purchasing this same product. So this means in the end of the first year, you pay $100 to purchase it. In the end of the second year, you pay $110 to purchase it. In the end of the third year, you pay $121 to purchase it. And it is going to increase like that. Such cash flow patterns are called geometric gradient series. Geometric gradient series. Or in short, geometric series. Now, in the uniform series, the cash flows in the end of every payment period is simply A. In gradient series, the cash flow that is paid in the end of year K is A0 plus K minus 1G, if you remember this from our previous lectures in the third chapter, basically. And in geometric gradient series, again, there is a base payment of A0 in the end of the first year, but every next year it is going to increase by 1 plus F factor based on the previous year. In the end of the kth year, the cash flow will be A0 times 1 plus F to the power K minus 1. And F is the average rate of change in the cash flow pattern, which is either an average increase or an average decrease. Okay, if F is positive, and this means the cash flow pattern, the cash flows in the cash flow pattern are increasing. If F is negative, then the cash flows are decreasing with, again, this geometric series. So let's see the picture. In the case where we have an increasing pattern, in the end of the first year, the cash flow is A0. In the end of the second year, the cash flow is 1 plus F times larger than the cash flow of the previous year. So A0 times 1 plus F. And in the end of the third year, the cash flow is going to be again 1 plus F times larger than the cash flow of the previous year. So it is going to be A0 times 1 plus F to the power 2. So every year, the cash flow is changing with a rate of F. Okay, with a rate of F. It is increasing by a rate of F, or if F is negative, then it means it is decreasing. In this case, we are going to see a picture like this, not like this, but it is going to decrease. But this is called a geometric series. As you can see, it is not linear. It is not linear, it is increasing geometrically. And in the end of the nth year, the cash flow is A0 times 1 plus F to the power n minus 1. Actually, this is a practical situation. For example, if you make a retirement plan, in a retirement plan, the people are not trying to get constant amount of payments in their retirement. In their retirement, every year, the total salary is going to do what? It is going to increase with a rate. Because you are going to be subject to inflation in every year, every worker that retires would expect a salary increase in the end of every year. And that salary increase in the end of every year is going to be by a percent F. So this geometric series is much more practical than the gradient series or the uniform series in real life. Okay? So the question is this: if we have such a geometric series of cash flows, what would be the principal amount that is equivalent to this geometric series, or what would be the future value of this geometric series? That is the question. Okay, so how do we define a geometric series? By the initial payment in the end of the first, which is the base amount A0, and the rate of change F, the average rate of change in each consecutive year, F.